be talking about some problems on in discrete harmonic analysis and in particular Fourier multiplier type techniques to approach these problems. Just like Sasha said, we're going to work in the parameter regime that's kind of familiar to theoretical computer science, high-dimensional probability. So here is just a warning in comparison from last talk. N is dimension, and B is degree. Apologies. And then, okay. So, and then we're working on the discrete n-torus, which I've written up here. Omega will be this fixed primitive root unity, and the n-torus is as written as omega sub k to the n. K, we're going to imagine being some small number like 7, so the regime you should have in your head is k less than d, which is much, much smaller than the number of administrators in American universities, or pixels in an image, depending on your taste. So yeah, so I want to talk about the way this question connects to classical harmonic analysis and also analysis of Boolean functions. So here I have written two classical inequalities, which I will instantiate in just a second, that both are known for the very standard setting of the actual n-torus, so morally sending k to infinity up there, but also for the hypercube, which is k equals 2. So to define Figiel's inequality, we need I'll call them M-level Rademacher projections. So F being, as I've written here, F is degree D. We define R sub n of F to be just the mth level of this polynomial. So we just sum over all multi-indices such that the L1 sum of the coordinates is m, and we take the coefficients, and of course the monomials. So these are, this notation I have just written up here for safekeeping. And with this Rademacher projection defined, Figiel's inequality says for the hypercube, so this is capital K is 2, it says that we have a dimension-free bound on the supremum norm. So every norm that I'm working with is going to be the supremum norm. So I'm just going to write the space. And right, so there's there's like now sharp estimates for what this constant is. The main point for us is that it is independent of dimension. And if you maybe
it's all L infinity.
No, omega 2 to the n.
Yeah, omega 2 to the n. Yeah.
Okay, and right, so the constant is well known, but for like this whole talk, we're just going to care about dimension freeness. We're not going to worry about what D actually is. But if you think about what might be known classically for the actual torus, there's such a comparison, but the constant is zero. So for degree D analytic polynomials, we on the torus, n-torus, we just have this. Okay. And so this is k equals infinity, sort of. Okay, another inequality, which has been recently applied very nicely to computer science and learning theory, is called the Boneless-Hill inequality, which is from von Hillen, 31. And it compares, again, for bounded degree polynomials, it compares a certain little LP norm of the Fourier coefficients in a dimension-free way to the supremum norm of f over the torus. Now, very importantly, this constant is sub-exponential in d, so there's a lot you can say about what we know and what we don't know about this d, but let it just be some constant for the purpose of this discussion. And much more recently, we also have this fact for the hypercube. Over d plus 1, f. Okay. And this is due to Defant, Monsieur, and Perez, DMP, much more recently, 2017. Okay, so we have sort of two endpoints of the torus. We have when k is 2, certainly k equals 1 isn't meaningful, and we have k equals infinity. And you can ask, well, you know, if we want to do things in the style of analysis of Boolean functions, maybe we could also ask for these inequalities somewhere in the middle. So what's going on here, and what's going on here for k strictly. And so it turns out that things are kind of difficult. So the proof ideas here and here are essentially the same. The proof ideas here and here are also roughly the same. But there's something about this setting that resists these proof techniques. So I want to illustrate that in the case of these Rademacher projections. Okay, so just very, very briefly to recall, so what's the proof for the polytorus? So f is some degree d polynomial. We're going to let z star be the maximizer of the inequality, zt torus. And then we're going to define a univariate polynomial q of t, which is just f where we attach t to each of the coordinates. T2. Okay. T is also on torus. And what we then do is we say, okay, this is some univariate polynomial of degree d. This is maybe making us think of a Cauchy estimate. So in particular, Rm f, or the norm thereof, is equal to the mth derivative of q at 0, which, this is by standard Cauchy estimate, is q of t is bounded with constant 1 by the supremum here. And if we remember where t is living, this is, of course, just at most on the polytorus. So, kind of immediate argument. Now, what changes if we go to the hypercube? 2 to the n. Again, we can write this, except our argmax will not be in the torus anymore. We'll put it in here. Sorry. And then our t is not going to live in the torus. Our t will be between -1 and 1. So the whole interval. And essentially everything is the same. We still have this supremum equal the derivative of q at 0. But this comparison is no longer with constant 1. This comparison has, so that this is now an application of Markov's inequality. So it has some, Chebyshev polynomial type inequality here as a function of d. And then what you notice, okay, so you have this polynomial which is univariate, and you're optimizing over t in this interval. Well, if we let our z's also go between -1 and 1, we get that the supremum, this guy here, is upper bounded by the supremum of f, not on the hypercube, but on the solid cube. So the interval -1, 1 to the end. And as a final and crucial step, we note that any function on the hypercube is multilinear. So the individual degree is only ever 1. And so f is kind of trivially convex. It's a multi-affine function, which means that the supremum over the solid cube is at most the supremum over our hypercube. So again, it's essentially the same amount of effort, but something breaks when we have k larger than 2. So if you think about it, like what comparison should we use here for larger k?
Say again what K means?
K is the number of points on the discrete torus. So k here, you see omega is k through unity, and capital omega is these grid of points in each coordinate. Yeah, so the kind of the problem is it's like really unclear what to use here, and you could, if you wanted to use a Markov Bernstein-type inequality, you could maybe optimize over like the convex hull of omega k, but then it's really unclear how to relate this back to the sparse grid of points. So essentially, this is just meant to be a brief illustration that things are not so easy. Like it's hard even just to project in the in the discrete cube. So what I'd like to talk about are some Fourier multiplier techniques for actually achieving this projection and much more. Any questions at this point? Okay, so what we're going to do is, so it seems hard to project onto the kth homogeneous part of f. So instead, we're just going to see if we can make any kind of projector at all, and then we'll bootstrap and get ever closer to the thing we want. So I just have a theorem for you. It takes a little bit of defining. So I'm going to define what I'll call prefactors. So for a multi-index alpha, and we're going to define tau sub alpha equal to j such that alpha j is non-zero, so indexing only over the support of the monomial of 1 minus omega, it's that omega there. So these are just some numbers, one associated to each monomial. And let's also define this thing that we call a support pseudo projection. So d sub L of f will be just the part of f where the support size is L. So by support of alpha, I mean the set of coordinates for which alpha sub the coordinate is non-zero. So, okay, and then it's not actually going to project onto this support homogeneous piece. It's going to do so with these prefactors. So tau alpha times alpha z alpha. Okay, it seems like kind of a strange operator to define, but it is nice for the following reason. So again, f is always degree d. We have that d sub L f is bounded in the way one would hope. So proof idea. So replace, what we'll do is we'll actually take inspiration from the hypercube projector. So we'll replace each zj, one of these coordinates, with actually two variables. So it'll be zj, but then it'll be times 1 plus omega over 2 plus 1 minus omega over 2 times a new variable xj, and xj will be in the hypercube. So with this replacement, we now get a new f, and it's from the discrete torus times the hypercube. And the important thing to note is that image, let me call this f twiddle. Image of f twiddle equals image of f. Why is that? Well, for any value, each of the xj's take on this sum here. It's either 1 or it's omega. So it at most rotates zj by something in this grid. So it's like immaterial from the point of view of image, which means we can easily think about how the supremum of this guy might compare to the supremum of f itself. And we can also look at what happens to a whole monomial. So it becomes j such that alpha j not 0 is to j alpha. So j, okay, xj. And you have to sit with it for a second, but what's kind of beautiful is that when you multiply this out according to alpha j, it just becomes the version where alpha j is sitting on top of each of these omegas. And upon further rearrangement, you see this is 2 times some factor depending on the size of the support of alpha times t sub alpha, so that's where this appeared, times j x. Yes. So with this modification of f, we see these t alphas naturally appear. And now that we have, plus, so there's more stuff. So I wrote down the like leading term in the x's. Of course, there will be some extra polynomial in x where the degree of x is lower. So so one thing to say here is in this monomial here, the power on x is, the degree of x1 through xn is equal to the support size of alpha. This is because for each j, where there's a non-zero alpha on z, we have one instance of xj. And so in this sense, this extra set of variables, it's just holding on to the support size of the monomial. It only records this. And then we have some junk. But the point is that the junk is of x order strictly less than the size of the support of alpha. So doing this change, it made some really, it took a single monomial and kept the, quote, leading term in x very nice and easy to understand, but it created some junk in the lower levels, in the lower degrees of x. And so then the idea is to use the projection on the support size of alpha from the hypercubes. So that's the idea. And yeah, so what this gives you is a way to argue this proposition for the part of f that has maximum support. So if you make this change for everything, and then you finally project where this is set to the maximum support size over all monomials, you'll get exactly this here. And then you just repeat the argument. So you've bounded the top piece, you can pull it away, it's triangle inequality, repeat, 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 and you get this proposition. Okay. Now, if we compare what this proposition does to what we would like, which is a projection onto the kth level, or kth degree, it has several deficiencies. I guess the two main ones being that it introduces some very strange prefactor, and then also that it's projecting onto like support homogeneous parts rather than parts that are standardly homogeneous in terms of degree. So we would like to essentially just see how much we can get with this. For instance, can we remove the tau sub alphas, or can we work towards saying something about projections onto degree? And so for now, let's take a goal of removing the tau sub alphas from D sub alpha. And yeah, so maybe I can ask you all. So if you're given a black box projection D sub L, and I can pick any L, and I get part of F, which is just the chunk of F that has support size L with some numbers that I don't want. Can we think of any ways to make a new projector where these T sub alphas are not hanging around? By the way, let me, yeah, so as a reminder, this is the T sub alpha. It is not unique to each monomial, so there are distinct alphas for which this is equal, but it's also, it's like hard to think about in too much detail. So, yeah, so I can give you the approach we took to resolve this, which is to say, okay, applying T sub L, it introduced these T sub alphas, we would like to remove them, so let's just apply it again. So, yeah, in order to see what happens, I will just make some definitions. So, I mentioned not all these T sub alphas are unique, so let's just call the equivalence class classes T1 through T R. And we'll just set it to the set of all T sub alphas, such that support alpha equal L. Okay, and then I just want a name for the chunk of F corresponding to what you get out of D sub L. So we'll set Gj equals the sum alpha such that support L, and also T alpha equals J. F hat is. Okay, so the point is we have R many distinct taus, and we're just naming the part of the homogeneous slice, support homogeneous slice, corresponding to having that particular tau. So what does this mean in terms of D sub L? It means that D sub L of F is equal to tau 1 G1 plus tau 2 G2 plus some stuff plus tau R GR. And I propose just applying this again. So dl squared F, this is not very interesting, but maybe you can imagine what might be the next step. Okay, so that doesn't seem to help immediately, but what should we do next?
Same thing.
Ah, brilliant, yeah. Brilliant. Did somebody tell you what to do? Okay, so let's just do this a ton of times. Let's do it all the way up to D sub R. No parentheses. LF times. So this is tau 1 R G1 plus tau 2 R G2 tau R GR. Okay, so now we have a huge number of monomials, none of which are what we want. Well, exactly. So if you look at this, these taus, you just, erase the g's, these taus form what's essentially a van der Waals matrix. It's like a modified van der Waals matrix. And what that says is that each of these polynomials, this polynomial, and this one, they're all linearly independent. And moreover, there are enough of them to span the space of monomials, to span the same space of monomials that's spanned by each of the G1 through GR individually. So what that means is not only can we define a D sub L as a polynomial, not only can we define a new D sub L as a polynomial of this D sub L which has no taus involved, we can pull out each of these G sub R's individually. And that's like a realization that we will make lots of use of. So where to record this? Okay, so we're now upgrading this D sub L to a better one, so I'm gonna erase it. And we have this defined up next. Okay. So this upgraded projector.
In principle, R could depend on N, right?
Yes, in principle it could, but it does not. And it does not because the degree is independent of N, and so the support size is independent of N. And so no, it's like really important. I haven't been careful tracking N dependence. So the question is, what are the distinct T sub alphas? How many distinct T sub alphas can there be? And it ends up being just a function of support size and individual degree. Okay. So let's define our improved guys. So define V sub L, so still projecting onto this support homogeneous piece, but now we're projecting onto a much smaller section, L tau sub alpha F, which is the sum over all those indices which are equivalent to alpha of this polynomial. So what do I mean by equivalent? There are two conditions to be equivalent. The support sizes have to be the same, and then the taus have to match. So yeah, so the point is each one of these projectors here, as we just argued, is equal to a polynomial of these projections here. And you can check the polynomial is nice. So all the coefficients are bounded, everything is good. We have the theorem we had hoped for. This much more granular projector is also bounded independent of divergence.
L here is just the degree of alpha.
L is the support size. Yeah.
Kind of, I was just trying to, the notation is slightly redundant.
Yes, thank you. Something. Yeah, you're totally right. Okay, so one thing that's a bit weird is that there are indices, alpha, that have different support sizes, but can have the same tau sub alpha. So this is why these are not entirely, yeah. No, it's a great question, thank you. Okay, so we have this guy, we can project onto these kind of funky support homogeneous sub pieces. And you know, it's like it's not clear yet where I'm going with this. I want to ask for your patience for one more fact, and then we'll see how this all gets involved in proving the thing we wanted at the beginning. So in particular, I want to study these classes of taus a bit more. So maybe just as a specific example, here's a case where they're equal for very different alphas. So let k be 3 and let alpha be 2, 1. I need 7 ones, so help me. How did I do? Good. And then beta equals 2, 2, 2, 2, 2. These are 2's. Okay. Turns out that so the support sizes are the same in particular in the way I've written them. The support size is n, but that doesn't matter for this example. But we do have that tau alpha equals tau beta. And the reason for that is this identity, 1 minus omega to the 7, 1 minus omega squared equals 1 minus omega, 1 minus omega squared to the 7. So it's like, it seems kind of annoying to figure out when these things are equivalent, but we can prove one fact, which is kind of nice. So if alpha and beta are equivalent in the sense of having the same support size and the same taus, then a monomial indexed by alpha and beta will be equal on a very specific point. So it will be equal on a point actually not on our torus, but on an enhanced version of our torus where we doubled the number of points. So let me see what I mean. So this is z1, z2, zn to the alpha equals the same thing Okay. This is, I guess, right now a little bit strange, but it is the key fact that we will use next. Okay, so the proof of like why this should. Oh, sorry. So square root of omega, I guess, is not unique. Just pick the smallest one. Pick. So if we're on the circle and this was omega, just pick this guy here, like the first root. Okay, so why could this be true? Well, it's true because of the following picture. So I'm going to consider the points actually, let me write the identity first. So it's true because of a fact that square root of omega to the k is equal to I times 1 minus omega to the k divided by the modulus. Okay, so this is, it seems like a strange thing to say, but we can draw a picture that I think is kind of nice. So let's just say k equals 5 for fun. So we're like, okay, let k go through all its possibilities. So, sorry?
Bisectrice.
We can just draw for all k what these points are. So I'm rotating it, so here's I, and if k is 5, let's say these are the points. And we want to divide by the modulus, so here are the rays. And I don't know, norm 1 guys are here, 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 and here. And it turns out that all these angles are the same, and they're equal to square root of omega. So we have this little geometric fact, and what that means for tau alpha and tau beta is, well, beta j. So if we take both of these guys and we divide by the modulus of tau beta times I to L modulus tau beta tau alpha times L, then what we do, so we were given, so this is tau alpha, this is tau beta, they're equal to each other, we just divide by the modulus and multiply both sides by this, and then apply the identity, and we get. So we now, like the full summary is that we have these granular support homogeneous projectors, and we know that when two indices fall into the same T alpha, they have this strange fact about like a half angle, or a half root of unity. Okay. And I have like 10 minutes? 20. Okay. So let me just record this proposition. Alpha implies that okay. So now let us return to our original goal. So we want these Rademacher projectors to be bounded independent of dimension. So these guys are projecting onto degree homogeneous types of F, not support homogeneous. So this is what we want. And Okay, so there are parts of this proof I don't have time to discuss, but let me just give you an outline. So the first observation is that it suffices to prove a discretization inequality of the following kind. The supremum of f on the entire torus is bounded independent of dimension by f on our original discrete torus. Why is that enough? Because if you'll recall from the initial discussion, we know how to make this argument over the torus. So the supremum on the discrete torus of the projector is certainly at most the same guy over the torus, which with constant 1 is bounded by f over the torus. What's torus? Well, okay, which finally, if we can prove this, gives us what we want. So, does that make sense? So, new goal, to prove a discretization inequality. And what?
But it seems like you just abandoned everything you were just talking about.
Yes, yes. So it turns out that this can be proved in 2 steps. One, let me write them down. So it's, okay. So 2 steps. The first step is to compare f over the torus, dk, with f over which discrete torus, not k, but 2k. It turns out that this argument is much easier than this one. I don't have time to discuss it. I mean, it's not like 3 sentences, but you write down a system of constraints, and you'll see it does work. And then we want this comparison. Okay, so this step I will not discuss, but it turns out that this fact here is exactly what we need in order to prove this comparison.
So for the first inequality, I mean, it suffices to consider k equals 1, right?
For the first inequality.
Yeah, the first inequality you wrote down there, or below, yeah, first inequality.
This one?
N equals 1.
K equals 1.
K equals 1.
Because, I mean, it's a bigger set, so k should
Suffices.
I mean, this kind of inequality that you're looking at is if you take a divisor of k, the right-hand side becomes.
But it's a polynomial. It's not multilinear polynomial anymore.
Yeah. So such a result is known for this, but it's only known for affine
Multilinear.
polynomials.
They should be on the hypercube. But these guys are not on the
The
hypercube.
individual degree here
Z1 can be to the power of
squared, cubed.
k minus 1, 5, 7.
Oh,
So it's a much bigger class of polynomials.
Yeah, thank you. Cool. Okay. So I claim that like immediately we have this. And why is that? Do we need notation anymore? Can I stop with the notation?
Sorry, the 2 is there. Yes. The f is anything on the torus, so this is f.
Yes. So f is deg f is less than d, and the individual degree, which I will define in a second, is less than or equal to k. So individual degree, I mean, view f as a univariate polynomial in any of the coordinates. What's the maximum like univariate degrees?
Because that's the answer to the question why it doesn't suffice to say k equals 1.
Exactly. Yes. Yeah. Okay, so maybe I can just say in words some of this. So we're going to let z star in 2k to the n maximize f. And so what that means is like for some coordinates of z star here, it's going to live on omega k. So it's going to be like a well-behaved point. And if that's true, we're just going to forget about that coordinate. It's like it didn't exist. The only problematic points, the only problematic coordinates for this comparison is when our point is living in this like half omega thing. So now we're going to assume for all j, zj star is in omega 2k without omega k. All right, and then I claim we can further assume something. So let's just take the triangle as our, so this is k equals 3. Let's say one of the maximum guys here is like -1. Well, I claim I can multiply z, just the coordinate zj, by an element of omega k to rotate this point to always be square root of omega. So this guy here is square root of omega, and I claim that no matter if my bad point is this bad point or this bad point, I can always multiply it by an element of the smaller group to bring it here. This should be like immediate. And so what this means is we can also assume that the maximizer has an explicit form. Z star is just square root of omega, square root of omega. Okay. So what we want then is that f at this specific point is controlled independent of dimension by the supremum of f at the smaller, over the smaller torus. And now we apply our stuff. So we split f according to this projector. We just split it into all possible things. And we note that f is the sum over j equals 1 to some constant number of guys independent of dimension of polynomials. And these have special features. So these g sub j, a, the absolute value at omega is actually equal to g1 and b, j, we have a comparison. What do I want to say here? So the point is that
Y is A?
yeah, y is a. Let me recall. Maybe I don't need that.
So you're plugging in that point, right, and you're on the same, so you can pull it out as a sum.
That's exactly what happens, but
Well, but this is for homogeneous. So the point. Okay. So the point is that this is true only for these very special ones, and sorry, I'm needing a second to recall why this is true. So what we claim is that for all, like here's how you prove this inequality. You want that for all alpha, beta, for all alpha similar to beta, we need that square root of omega to the alpha equals square root of omega to the beta, because then you can pull it out. And that's exact, we should have this already, right? Yes.
So it
Okay.
goes outside. Okay.
So it pulls outside. So this is like a very, it's like two sides of a bridge have been crossing a chasm and barely touched. So we got these really strange projectors that chop the polynomial up into these little pieces, and they're just small enough that this fact is true, that this like half of omega point is equal for any monomial in the same chunk. And that is precisely what we needed. That's like just enough to compare f at this point with f over this smaller torus. So maybe another thing that's kind of fun about this argument is that eventually, okay, now, like, so claim we're done. Now we have gotten our Rademacher projections for the discrete n-torus, and we used both of the projections from the hypercube, which was to build the original support homogeneous projector, and then much more recently, we also projected on the torus. So it's like, yeah, somehow we made stuff in the middle by using tools from both extremes. Okay, I think that's enough time. I promised some connection to number theory, but if somebody's curious, feel free to ask. Otherwise, yeah, no problem. Thank you so much.